Welcome to a course on complex analysis. In this lecture, we are going to start our discussions on zeros and poles. Without any delay, let us see what the theorem tells about. Here we have two functions. Both the functions are analytic at a point z0. Right? Your function p is not equal to 0 at the point z0 and q has a 0 of order m at z0. So which means your q as a 0 of order m means by the theorem that we have studied in one of the previous lectures, we can write your q of z as z minus z naught to the power m multiplied with some other function of z, and this is not equal to 0 at z naught, and this function is also analytic, right? Then the quotient will have a pole of order m at z naught. So this is what we'll have to prove, right? Let us get into the proof. So this is quite easy. Let just a minute, let me check. I have a page. Okay, we'll have to complete the proof in this page itself. Okay, fine. So let's p. Okay, actually it is given p and q are analytic functions. Analytic functions at z naught. P of z naught is not equal to 0, and q of z takes this form. That is, it has a 0 of order m, where your phi of z naught is not equal to 0 and phi of z is analytic as well, right? So this is how we can write. Now your p of z upon q of z, this is simply p of z upon z minus z naught to the power m multiplied with phi of z. Here let me just write p of z upon phi of z upon z minus z naught to the power m. Okay, so the numerator part, let me take it as some psi of z upon z minus z naught to the power m. Here the psi of z is p of z upon phi of z. Since phi of z naught is not equal to 0, psi of z is analytic at z naught. Since both p and phi are analytic at z naught, and also phi of z naught is not equal to 0, we can come to a conclusion that this psi of z is analytic at z naught. Okay, therefore this p of z upon q of z has a pole of order m at z naught. From this, how did we come to this conclusion? For which you just expand this is analytic at z naught, then you can give Taylor series expansion. Okay, Taylor series expansion, that will have your psi of z equals psi of z naught plus summation n runs from 1 to infinity psi nth derivative at z naught upon n factorial multiplied with z minus z naught to the power n. So this is what you are going to have. When you just multiply this one with 1 upon z minus z naught to the power m, you would have this is the largest thing till if I'm not wrong, mth derivative would be the constant term, right? And then you will have m plus 1th derivative at z naught upon m plus 1 factorial 1 and then plus etc. So from the definition of a pole, it is very obvious that this function has a pole of order n. This actually completes the proof. Okay, if you know what do we mean by the definition of a pole, it is very obvious, right? Here we are going to see an example. Let p of z equal 1 and q of z equal z multiplied with e to the power z minus 1. Okay, both these functions are entire. Okay, now let us see the zeros of q of z. Q of z may be written as z e power z 1 plus z upon 1 factorial plus z squared upon 2 factorial, etc., then minus 1. So this is nothing but z upon 1 factorial plus z squared upon 2 factorial plus etc. So when we take z as a common thing, then it is z squared 1 plus z upon 2 factorial plus z squared upon 3 factorial plus etc. So when we just equate this to 0, it is very obvious that z equals 0 is a 0 of order 2. Okay, so actually from this itself we can directly say z equals 0 is a 0 of order 2. Now let us write p of z upon q of z, which is 1 upon z. Actually this function has a pole at z equals 0 of order 2. This can be examined with that help, right? So if you have some quotient rational function, you can just equate your denominator to 0 in order to find out the zeros. Okay, count for the orders as well, right? That is how many times the zeros are repeating. If you just find out the zero of an order, then the rational function, that is the quotient function, will have a pole of order that value at the specific point, right? Now let us move to the next theorem that tells us if p and q are analytic functions at z naught and your p of z naught is not equal to 0 and q of z naught is equal to 0, q prime of z naught is not equal to 0. So with which what can we interpret? Okay, given p and q are analytic at z naught. Okay, also given p of z naught is not equal to 0, q of z naught equals 0, and q prime of z naught is not equal to 0. By the definition of zeros, q of z shall be written as z minus z naught multiplied with some q1 of z, right? Some q1 of z, or if you want some other notation that you can give, let me write it as g of z, where your g of z naught is not equal to 0 and this is analytic, right? You have the function to be equal to 0, but the derivative, the first derivative itself is not equal to 0. That clearly tells us that it has a 0 of order 1 at z equals z naught, right? So by the definition of a 0 of order m, we have just written down the equivalent form of q of z, right? So now by uh, we know that then this P of Z upon Q of Z shall be written as P of Z upon Z minus Z naught multiplied with G of Z. So this is P of Z upon G of Z upon Z minus Z naught. Clearly, this P of Z upon Q of Z has a simple pole. So this is one of the claim, that is what we obtained. Now we'll have to find out the residue value, right? So in order to find out the residue, uh, okay, for which let me take this entire part to be some phi of z, right? So now my p of z upon q of z is in the form of phi of z upon z minus z naught, right? Now let us calculate the residue value. Residue of z equals z naught p of z upon q of z. What is the residue value? The residue value means we'll have to expand this function in a Lorentz series and we'll have to look for the coefficient of 1 upon z minus z naught, right? So if you just look for that value, you would get what? Let us see now, right? So since, okay, let me not, that is not actually a part of this proof, but for your ideology, let me give you here. Since phi of z is analytic at z naught, your phi of z shall be written as phi of z naught plus phi prime of z naught upon 1 factorial z minus z naught plus etc. Okay, this one upon z minus z naught just gives you phi of z naught upon z minus z naught plus phi prime of z naught upon 1 factorial plus phi double prime of z naught upon 2 factorial multiplied with z minus z naught plus etc. Here the coefficient is what? Simply phi of z naught, right? So this is equal to phi of z naught. What is phi? It is p of z upon g of z, that is equal to p of z naught upon g of z naught. We just have to evaluate what is this g of z naught. Okay, let us evaluate that as well. So by this z minus z naught, so this is what we have. We have to evaluate what is g of z naught. We do not have this term separately. Okay, let me just differentiate this one. Q prime of z equals z minus z naught multiplied with g prime of z plus g of z. Am I right? So from this I can deduce very well what is g of z naught. So that is q prime of z naught equals z naught minus z naught multiplied with g prime at z naught plus g of z naught. So this is 0 since z naught minus z naught is there. This tells me that my g of z naught is nothing but q prime evaluated at z naught. So therefore this quantity is nothing but p of z naught upon q prime evaluated at z naught. Okay, suppose from this if you try to deduce what is g of z, it is q of z upon z minus z naught, right? When you try to evaluate it, you would get indeterminate form. You cannot directly evaluate it. That is why I have just differentiated, and from that I was trying to get the value. This completes the proof actually, right? Now we have few examples which are applications of the theorem that we have just seen. So let us see one by one. F of z equals cot z. If you are asked to find out the residue of this function, what you can do is that you just equate your denominator to 0 and find the poles of it. If that is a simple pole, that you can very well make use of it. Okay, in order to find the residue value, I have just made use of the definition here with which I have found. If not, you can very well make use of the property or the result that we have studied as well. Just a minute. Okay, that we will see in the later part. So this cot z cotangent of z may be written as cosine of z upon sine z. So for which let us find out the poles. The poles of f of z are given by sine z equals 0, which tells us that z equals n pi. Okay, all these are simple poles. So if they are simple poles, then we can just calculate it easily, right? For which what should we do? First of all, it is written in the form of p of z upon q of z. So we'll have to identify, we'll have to differentiate q of z. So here q prime of z is what? Simply cosine of z, right? Your p of n pi, that is cosine n pi, which is minus 1 to the power n, and q prime of n pi, which is also cosine n pi, that is also minus 1 to the power n. Therefore, residue of this function at z equals any n pi f of z is minus 1 to the power n upon minus 1 to the power n, which is equal to 1. Right? The next example is we have f of z equals tan hz hyperbolic tan z upon z squared. Okay, here you may simply look at this function and decide z equals 0 is the only pole of order 2. In that case, what are we going to do? You may think that way, but that is not the case. Your numerator can also be written as a quotient function, that is sine hyperbolic z upon cos hyperbolic z. So we'll have to do that as well. So it is hyperbolic sine z upon z squared multiplied with hyperbolic cos z. Right? We can write like this. So here, what are the zeros of the denominator? Let us take this as p of c and q of c. The zeros of q of z are what? So z equals 0. That is one thing. Z equals 0 and z equals pi I upon 2. Okay, if you just equate your cosine hyperbolic cosine z equals 0, this is what you are gonna get, right? So after which what should we do? We'll have to, okay, among this is a double pole. These are, this is simple pole. Now let us just evaluate the residue at simple pole, right? So for which what should we do? We'll have to, that is sine hyperbolic of pi I upon 2. So what is this value? This value is iota times of sine pi upon 2, which is iota, that is not equal to 0, right? And now we know that q of pi I upon 2 is 0. Now we'll have to find out q prime. What is q prime here? So q prime of z is z squared sine hyperbolic z plus 2z cosine hyperbolic z, right? So q prime at pi I upon 2 is pi I upon 2 whole squared sine hyperbolic of pi I upon 2 plus 2 pi I upon 2 multiplied with cosine hyperbolic of pi I upon 2. So this quantity is 0. So we are left with minus pi square upon 2, and this quantity is going to be equal to I. So minus I pi squared upon 2. Therefore, residue of z equals pi I upon 2 to the function f of z is, what is its value? Iota upon minus iota pi squared upon 2. So it is going to be equal to, just a minute, did I make some mistake? Yeah. So this is 4, right? When we square 2, we would get 4. So this is minus 4 upon pi squared. This is the value, right? So, sorry. And the next example is, we have this function f of z equals c upon z squared plus 4, right? So here your p of z is c and q of z is z squared plus 4. It is very obvious that when you equate your q of z to 0, you would get z squared plus 4 is 0. That tells you z is plus or minus 2i. Both these are simple poles, right? Now let us differentiate this one. This gives us 2z, therefore q prime at 2i is 4i, and q prime at minus 2i is minus 4i. Therefore, residue of the function at z equals 4i is, yeah, we'll have to evaluate p of z as well, right? So p of 2i is 2i, and p of minus 2i is also minus 2i, right? So this is 2i upon 4i, which is equal to 1 upon 2. Similarly, residue z equals minus 2i, actually. Yeah, 2i minus 2. F of z is minus 2i upon minus 4i, which is equal to 1 upon 2. That's it. So they are quite simple, right? So the thing that I was trying to say is, if okay, in order to prove the theorem, we have just made use of the actual definition to prove. I was trying to say there are another way in which also we can define. That is, if your function, if you say your function as a pole of order m, then you can write your function in this form, and also the residue of the function at z equals z naught, this may be found as phi of z naught for simple poles. Okay, and this, if it is not a simple pole, then the residues are found using the derivative if m is bigger than or equals to, right? So this is how we found the residue value. This is one way of finding the residue value, but the actual definition is the coefficient of 1 upon z minus z naught, right? You can make use of either of the thing to prove this theorem. Thank you.